All right, as we continue into circular motion, remember centripetal forces. Any force that causes an object to move in a circle is called a centripetal force. And any force can be a centripetal force if its action causes an object to move in a circle or even curve. Centripetal forces always point to the center of the circle. So if I'm swinging this around my head, centripetal force is toward my hand. Tension is providing the centripetal force. It's also accelerating inward, and therefore its velocity would be tangential or perpendicular to it. Notice we've got this little picture right here. The force exerted on the whirling can is toward the center. There is no outward force acting on the can. We'll talk about that here in just a few minutes. So when I talk about velocity and centripetal force, the direction of the velocity and the centripetal force may change as it spins around. So we're just reiterating this. If this is spinning around here counterclockwise, that the velocity and the centripetal force directions change, but they will always be perpendicular, tangential to each other. So in the picture here at A, the net force is inward, right? The centripetal force here, this would be tension providing the centripetal force. The velocity is perpendicular to it, so it's to the left. And at location B, centripetal force is inward, velocity is tangential or perpendicular. And at location C, still moving around in this counterclockwise location, centripetal force is inward and velocity is perpendicular to it. So now we're going to look at the math behind it. So here we can look at centripetal force and radius. And I'm going to be using this equation here, and this is the math behind what we are going to be looking at. That's the centripetal force is equal to the mass times the velocity squared divided by radius. So centripetal force equals mv squared divided by r. So centripetal force is inversely proportional to the radius of its circle. In other words, the smaller the circle, the greater the force needed to continue circular motion. And by doubling the radius of the circle, one must provide 1/2 of the centripetal force. And if we tripled the radius, it would only need 1/3 of the force. So we're looking at relationships here of the radius to the centripetal force. So here I have the inward force, right? My centripetal force here of 1 Newton. I have a radius of 1 meter. I have a mass of 1 kilogram, and it has a velocity of 1 meter per second. If I double the radius distance to 2 meters, right, from 1 meter to 2 meters, a 2 meter radius decreases the required centripetal force to 0.5 newtons. So I can use these values to solve for this. So if I'm looking at this in terms of the math, we're kind of talking both mathematically and conceptually. So let's look at the next one. Centripetal force and mass. Centripetal force is directly proportional to the mass. The larger the mass, the more force is needed to keep it moving. By doubling the mass, one must double the necessary centripetal force to keep the object moving in a circle. So here I have a 1 kilogram force, 1 kilogram mass. I have a 1 Newton force. It's a 1 meter radius, and it's traveling 1 meter per second. If I double, in this case here, if I double the mass, I must double the force necessary to keep this 2 kilogram object traveling at 1 meter per second with a radius of 1 meter. So we're looking at relationships here. We're going to start plugging in numbers here very soon. So centripetal force and velocity. So centripetal force equals mv squared divided by r. Centripetal force is directly proportional to the square of the object's linear speed. Doubling the speed requires 4 times the centripetal force. Right? If I double the velocity, 2 squared is 4 times the centripetal force. So here I have a 1 kilogram mass. It's traveling at 1 meter per second, and it only takes 1 Newton of force at 1 meter radius. If I double the velocity, right, all things being the same here, 1 kilogram mass at 1 meter, it quadruples the force necessary. So 2 meter per second speed increases the required centripetal force to 4 newtons. So the relationships that we're looking at are, how does centripetal force change if mass changes, if velocity changes, or if radius changes? So we're looking at relationships here. It's inversely proportional to the radius. It's directly proportional to the mass. And it's directly proportional to the square of the object's linear speed. So when we move into how gravity works, right? Gravity can provide the centripetal force. The math gets a little bit more complex, but it's nice we're not going to be having to solve problems. We're simply going to look at the ratio, where the gravitational constant is capital G. It's 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. So it's a funky number, it's a funky unit. We'll talk a little bit more about that in class. But it's essentially this tiny number times any two masses that are at some distance. But notice, m1 is the mass of some object, and m2 is the mass of another object, and r squared is the distance between the masses. So the force of gravity changes, right? Masses stay constant. So think about your weight. It'll change. Your total mass will remain constant. If you look at the formula above, the gravitational constant, g, is very, very small. It's extremely tiny. So therefore, as weird as this may sound, you have an attraction, a gravitational attraction to every one of your classmates. And here's how. Here I could identify this whether we're talking students or we're talking planets. Well, here it'd be a moon orbiting the Earth. That the moon has a mass, the Earth has a mass. That the centripetal force, or the force of gravity, is going to be proportional to g times the mass of the moon times the mass of the Earth divided by the r, distance squared. So as I look for centripetal force and gravity, how does it relate? Well, gravity is a very weak force, right? It takes this tiny number here that if we look at g is 6.67 times 10 to the negative 11th power, that's a tiny number. It takes a very large mass to create a gravitational force. And gravity is based on two masses and their distance away from one another. So mass and the force of gravity. Any two masses have a force of gravity between them. If I double the mass, I have twice the force. If I double both of them, I have 4 times the force of gravity. So objects orbit, right? We call them satellites. That really, this is still an extension of projectile motion. That the path an object takes in its orbit is typically elliptical or oval shaped, but it can be circular. An object moving in an elliptical orbit does not move at a constant speed. Instead, it moves faster when it's closer and slower when further away. So check this out. If I look at this picture right here, if an object is launched fast enough, it will orbit due to its continued falling into the Earth. If it's not launched fast enough, it will fall back to the surface of Earth. So these are projectiles. If it's launched at the correct velocity, technically the escape velocity of Earth, 8,000 meters per second, it'll just continue orbiting the Earth. So before we completely tie this up and get into the loose ends of what we have going on here, we're starting to get into the math, and the math is kind of the key part here. The last topic that we're going to look at with astronomy are called Kepler's laws. There's 3 of them. Kepler's first law is called the law of ellipses, that all objects, all celestial bodies, move in elliptical orbits. They are not perfectly circular. And because of this, the radius at different locations changes. A perfect circle versus an ellipse. An ellipse is like an elongated circle. The second law, Kepler's second law, the law of equal areas, says that as planets orbit in equal time sections, so each of these time sections over here, right from here to here, from here to here, the areas are equal. This means that when an object is closest at this position called perihelion, it travels faster to make up for the smaller radius. The converse is true too. When a planet's further away from the body it orbits, called aphelion, it travels slower. And we'll be unraveling this mystery in the next couple days. But the idea here is that equal areas are in equal times. That if this were a pizza slice, this would be the same total size, well, technically area, as this pizza slice. And Kepler's third law, the squares of the periodic times, right, p squared, are to each other as the cubes of the mean distances. These are measured in astronomical units, or Earth distances, in 150 million kilometers, the average distance from the Earth's sun. So p is the period in years, and r is the radius in AUs, which is 1 AU is 150 million kilometers. So period squared equals the radius cubed. And we'll have plenty of time to sort this one out. There you have it.